This tutorial will show some of the powerful tools CSI Bridge offers for the sophisticated modeling and analysis of bridges. The bridge we will model will be a 200-foot long concrete box girder with 2 spans, with a deck 36 feet wide and a depth that varies as a parabola. It will support 2 lanes of traffic, each 14 feet wide, and it will be pre-stressed in the girders of the concrete box section. Lanes and vehicles will be used to generate both influence surfaces and a multi-step live load analysis. The bridge is made up of abutments at each end, along with 3 columns and a bent cap at midspan. Tendons are draped in the girders of the deck, and the box section is modeled with shell elements. To start the model, we go to the Application button, or orb, and click on the New command. We set the units to kip feet, and click on the blank button since we will not be using a template. One option to use when developing a bridge model is to use the Bridge Wizard. And a quick check of the wizard shows that it lists each item and component in the bridge model, along with a description. As you step through the wizard, you may choose to define or modify your data as appropriate. However, for this example, we will not use the Bridge Wizard, but will instead create our bridge model directly from the commands on the ribbon. Typically, when developing a bridge model, one would step through the tabs in a left-to-right manner. The majority of commands that we will use to create the bridge model can be found under the Layout, Components, Loads, and Bridge tabs. The Home tab is used to set views and displays. And to select items. We start the process by defining a layout line under the Layout tab, which provides the primary control geometry for our bridge. We start by clicking on the New button in the Layout panel. We will specify a starting station at 0 feet and an ending station at 220 feet. The layout line is slightly longer than the actual 200-foot bridge to accommodate skews. By using the Quick Start option, we can quickly define the shape of the horizontal layout. For our model, we will use straight line geometry. Note that the layout line is now available on the drop-down list, and that the Copy, Modify, and Delete buttons are now active. With the layout line geometry defined, the next step is to define our lanes using the New Lanes command. Because our model has been generated from a layout line, we will use the same layout line for the lane definition. Our first lane will be offset -9 feet, and all lanes will be 14 feet wide. We will define the lanes beyond the ends of the bridge. We can change the display color so that it is easier to see the lane. The center line of this first lane is shown relative to the layout line. Our second lane will be offset 9 feet on the other side of the layout line. Again, we will change the display color. If we go to the Home tab, and then the Display panel, we can view the lane width rather than just the center lines. Next, we go to the Components tab. This tab is organized into 3 sections: Properties, Superstructure, and Substructure. In the first panel, we can define and modify material and section properties. We will use the defaults for the materials, so no changes will be made. We will return to this panel later in the tutorial to add additional section properties. The next panel is where we will define the superstructure. We start with the deck section, select the deck section command, and then click the New button. Here, the program offers numerous parametrically driven templates, and we will choose a concrete box girder with vertical sides. Verify that the total width is set to 36 feet and that the initial depth is set to 5 feet. Scroll down to view the other dimensions. Next, we will define the vertical diaphragms that will be placed at each end of the bridge deck. Click the Item button in the panel once again, and this time select Diaphragms. Note that the button icons change, and click the New button. As our bridge deck is concrete, we will use the solid option with the default thickness of 1 foot. In this next step, we will define the parabolic variations of the deck depth, or how the deck depth increases over the span. This is done through the Parametric Variations command. Click the New button once again. We will have 2 different variations, one for the left span and a second for the right span. The depths will vary by a total of 5 feet and will be constant for 10 feet on each side of the bent. We have now finished the variation for the left span, and we'll move on and use a similar technique for the right span. With the superstructure items defined, we go to the next panel where we can develop the substructure. Start with the bearings by selecting the Bearings command and then click the New button. These bearings will be placed under the girders on top of the abutments at the bridge ends. We can use a previously defined link property or bearings that we define on this form. For this model, the bearings will allow translation along the layout line, but not in the other 2 directions. Continue with the substructure by clicking on the Foundation Springs command and then the New button. We will change the name to make it easier to identify. Again, we can use a previously defined link property or define the springs directly on this form. For this model, we will fix the foundation in all 6 degrees of freedom, but could easily specify an explicit stiffness or remove the restraint if so desired. Next, we will specify the abutments. However, before we do this, we need to define the concrete section to be used for the abutment. Go back to the first panel and click on the Type button and select the Frame Properties command, and then click the New button. Set the frame section property type to concrete and select the rectangular button. Name the section abutment and we will specify a depth of 8 feet and a width of 4 feet. Now we go back to the substructure panel and make sure that abutments is the selected item and click on the New button. The girder support can be either integral with the girders or connect to the bottom of the girders. For our model, the girders will be supported at the bottom. The bearings supporting the girders can rest directly on the foundation springs or on a continuous beam that is supported by foundation springs. For our model, the bearings will be supported by a continuous beam 30 feet wide, and the beam will be assigned the abutment section properties and will be supported on the foundation springs that we previously defined. The last item in the substructure group that we will deal with will be bents. However, before we work on this, we will define columns and a bent cap. Again, we go to the Properties panel and verify that the Frames command is selected, and then click on the New button. Verify that the property type is concrete and click on the Circular button. We will define a circular column that has a diameter of 5 feet. Click the New button again, and then the Rectangular button. We will define a bent cap with a depth of 10 feet and a width of 5 feet. The depth will match that of the deck, and the width matches the columns. Now that a column and bent cap section are defined, we can go to the substructure panel and specify the bent. Select Bents, and then click the New button. Similar to what was done for the abutments at the bridge ends, we need to specify how the girders are to be supported at the bent. However, unlike the abutments, the support will be integral at the bent. Verify that the cap beam is 30 feet wide and the bent will have 3 columns. The cap beam will be assigned the bent cap section that is 10 feet deep. Clicking on the Modify Column Data button, we can specify the column sections and locate the columns at 2.5, 15, and 27.5 feet along the bent. We will also vary the height of each column. Note how the columns are located. We will leave the column base supports as fixed, and the moment releases at the top of the columns will also be fixed. Last on this form is the bent type, single for continuous, or a double bearing line if the bridge is discontinuous at the bend. For this model, we will use a single bearing line. We are now finished with the superstructure and substructure definition, and we'll move on to the Loads tab. We start by defining the vehicles that will run on the lanes by clicking on the Type button in the first group, selecting Vehicles, and then clicking on the New button. In this case, we will use a standard vehicle, a HS20-44. The next step is to assign the defined vehicle to a vehicle class. Vehicle classes allow you to group more than one vehicle together for the bridge response. Next, we click the Load Patterns button to add a pre-stress load pattern. This model will not have any other applied loads, so we may move on to the Bridge tab. It is on the Bridge tab that we assemble the components we have defined into a bridge object. We start by clicking on the New button. Our bridge object will be based on the previously defined layout line, and the Modify Show Assignments area shows us what items can be placed and modified in the bridge object. We begin by defining the bridge object reference line. We'll move the abutment 10 feet in from the end of the layout line. Next, we will add a bent at midspan. Lastly, we will move the right abutment 10 feet in. Next, select Abutments and click the Modify Show button. Choose the Start Abutment tab, and we will rotate the abutment 15 degrees. The superstructure will have the previously defined vertical diaphragm and a substructure using the abutment's beam. Set the top of the abutment to 6 feet below the deck elevation. We will use the previously defined bearing property for our bearings, and we will locate the bearing 5.5 feet below the deck. The bearing will not be rotated from the layout line. Select the End Abutment tab and make the same changes as done with the Start Abutment. Note that the abutments have been rotated. Next, select Bents and click the Modify Show button. The bent will be located at the end of span 1 and will not have a diaphragm property, as the bent cap is to be integral with the deck. We will also rotate the bent 15 degrees. And the bent will have an elevation of 0. To fix the bent to the deck, we will define a new bearing called Fixed. This bearing will be fixed in all degrees of freedom. Note that the bent is now skewed as well. All the items defined up to now have been part of a bridge object definition. In order to convert these definitions into an object-based model, we need to link the model, which is done by clicking on the Update button in the Update panel. The CSI bridge model may be created as a spine model with frame objects, or with area or solid objects. In our case, we will be using the area objects. CSI Bridge has taken our bridge object definitions and created a structural model with area objects and supports at the left end, the midspan, and the right end. Next, we will add in the parametric variations to the deck span. We can do this by going back to the bridge object panel and clicking the Modify button, and then selecting spans from the assignments list. Or we can simply click on the spans button. Double-click under Section Varies for span 1, and we will change the total depth from constant to varying based on the previously defined parametric variations. Repeat this process for the second span using the other parametric variation. In order to see the depth variation better, we can switch to an elevation view by going to the Home tab in the View panel. We can also extrude the model for a different look. Returning to the Bridge tab, we will define the pre-stressed tendons. Click the Pre-stressed Tendons button, and then click the Add New Tendon button. The load pattern will be pre-stress, and the tendons will span the entire length of the bridge. The tendons will be post-tensioned with an area of 10 inches square and a force of 500 kips. They will be modeled as loads. For the vertical layout, we click on the Quick Start button and choose a parabolic shape. We will accept the default layout and we can now see the tendon position over the entire length of the bridge. Next, we copy the tendon just defined to all of the girders. Note that the original tendon, 10-1, will be deleted. If we click on the Show All Tendons button, we see in the section view how the tendons vary along the span. If we remove the area objects from our view, we can see the location of each of the pre-stressing tendons. Our bridge object is now complete, and we are ready to move on to the Analysis tab. In the Load Cases group, the drop-down list shows that 3 load cases have been defined: dead, modal, and pre-stress. To these, we need to add a moving load case. To do this, click the Type button and select the Moving Load command. And then we click on the New button. Our new moving load case will have our vehicle class applied to all lanes with a factor of 1. Clicking on the Bridge Response button allows us to select what moving load case results are to be saved. In this case, we will shut off a few of the element types not needed. We are now ready to run the analysis. However, before we do, we will change our display so that it will be easier to see the results. Back to the Analysis tab. We now click the Run Analysis button and set the modal case to Do Not Run. Upon completion of the analysis, the deformed shape for the dead load case is displayed. Next, we will display the deformed shapes for the other load cases by going to the Home tab and the Display panel. Note that for the pre-stress case, the displacement is in the up direction as expected. We can also plot influence surfaces for the moving loads. Here, we will plot the axial force response in a column for both lanes. Next, we will plot the bridge forces along the length for the entire bridge. Now we will unlock the model to allow us to define a multi-step load pattern for trucks, where a specific truck movement can be defined. Going to the Loads tab and clicking the Load Patterns button, we will add a case called Trucks with a type of Bridge Live. Clicking on the Modify Bridge Live Load button allows us to define our loading patterns. We will load the bridge with 3 trucks, the first being in lane 1, moving at a speed of 40 feet per second. The next truck will be in lane 2, starting at the opposite end of the bridge, moving in the opposite direction at 40 feet per second. The third truck will again be in lane 1, but will start 1.5 seconds behind the first truck. We will set the total loading duration to 7.5 seconds and discretize at 0.3 seconds. We are now ready to once again run the analysis. However, this time we are interested in the results for only the truck's case, so we will set all of the other load cases to do not run. As done for the previous load cases, we can view the bridge forces for the truck's case. We can also plot the stresses in the shell elements. Here, we will display the F11 component at step 9, which is close to midway in the analysis. Lastly, we will go to the orb and use the Create Video command to plot the trucks moving over the bridge. Make sure that the truck's load case is selected, and we will increase the magnification factor so that the deformations will be obvious. We also want to use the Show Vehicles option. The program shows the steps as it creates the movie. The AVI file can then be played in any AVI player. This concludes this tutorial.